Well, welcome to the third of the four videos that we have for this week. The topic we need to do this time is what I call What Else Is There? You guys know that we have covered a lot of stuff in statistics. Over the course of this semester, we've at least touched on every single chapter in the book. Some of them we have looked at in detail and done pretty much everything that's there. Others I have purposely skipped some things as we've gone through those chapters. Some of you also know that there are other statistics courses that you could take after this one. In fact, if you are a business major, a lot of times you have to take one or two other stats courses. And you might wonder what sort of things might you end up with there. Well, that's what we're going to try and answer in What Else Is There? Now, I know that what you guys are going to say when you see a topic like this is, do I have to know this? Do I actually need to do anything with it? And the answer is sort of, but not a whole lot. What's going to happen when you get to your fourth test with this is you're going to see a list of the different topics that I'm going to talk about here in the next few minutes. And I'm going to ask you to pick two or three of those and just write about a sentence telling what it's about. You don't need to know things inside and out because obviously you won't. There's a reason why we haven't covered it. But I do want you to have some clue as to what some of these other topics are. The first thing we're going to look at is what's called a standard deviation chi-square test. This is actually one of the topics that is in your book, but we skipped over when we were doing the chapter on chi-square. I very briefly mentioned it at the end of last week's video, but didn't really say anything about it. A standard deviation chi-square test, what you're basically looking at is the standard deviation bigger than it should be? Is it too big? What that would mean is that for one reason or another, your data is too spread out. The place where that mostly matters is in the field of quality control. In industry, any product that you make, there's going to be a very slight variation between each one that comes off the line and the next one. You're never going to find two things that are exactly the same at the microscopic level. Usually a small bit of variation doesn't really matter at all. But if it starts being a lot of variation, that can be a problem. And that idea of being too varied is exactly what I mean when the standard deviation is too big. Things are too spread out. Now, in the real world, what people usually do is they'll have a little chart like these ones that you're seeing, where they track things periodically. And if it goes outside like the red boundary lines on the one on the left, that's their clue that something's gone wrong and we got to make an adjustment. Sometimes you'll see multiple sets of lines. Usually the ones that are close to the middle are okay. If you go a little bit out, you need to watch things more closely. And if it goes clear to the end, then we've got a serious problem. So again, a standard deviation chi-square test, if you want to choose that one and tell me what it is, the key thing is you're asking, is the standard deviation too big? Is it too spread out? The second of these topics is something that's actually been in the news a lot just lately, and it's what's called high-power tests. The thing about a high-power test is that it's a test that is unlikely to overlook a significant result. If you've got something that didn't happen by chance, it's going to tell you this is significant. Now, the reason this has been in the news lately is that people have been looking for a medical test that's quick and easy that will identify whether people have the coronavirus. There have been tests for coronavirus for quite a while, but the problem is they're relying on DNA and it takes days to do that. They recently released a blood test that does give quick results, but the issue they found with it is that it has what we call false negatives. About 15% of the time, people that actually do have the disease, this test will come back saying they don't. And if you think about it, that's kind of a problem. If you actually did have COVID-19, but you didn't know it, You could go around and infect the whole community, and that is not a good thing. So they've been working on trying to develop a high power test that's also quick and easy to administer. And hopefully, before too long, we'll have something, but unfortunately, it's not there yet. A high power test doesn't have false negatives, or extremely rarely will it have false negatives. The problem with a high power test is that it does produce what we call false positives. This would be like a test that tells you that you do have coronavirus, but you're really fine. And that can also be a problem, but it actually is usually a little bit less of a problem. With most medical tests, what doctors try to do is start with a high power test. And then if that comes back positive, what they'll do is give a different test to confirm it. If both of those tests are positive, then they go ahead and start treatment. Key thing about a high power test, though, is it's not going to ever overlook a significant result. The third one is another thing that we skipped over in the book. This is actually in the chapter that has chi-square in it. It's what's called analysis of variance, or sometimes it's just called ANOVA. It can also be called an F test. The thing about it is you compare the mean and standard deviation of more than two samples. We've looked at things like men versus women, or blacks versus whites, or one group versus another group. It's not too hard to do like a t-test to compare two groups. But what if I didn't just want to look at blacks and whites? I wanted to look at blacks, whites, Asians, Hispanics, Native Americans, all the different possible groups that I could look at. Well, with what we've done so far, the only way that we could do that is to run a whole bunch of different t-tests. You'd have to look at every possible pair, compare them, and then look at that whole mess of different t-tests. And if you have very many samples, that can rapidly get to be a lot of tests. What analysis of variance basically does is it's like it's running all of those tests at the same time, but just in one test. The trade-off with that, and it really is the reason why we skipped the topic in the book, is that it becomes a lot more complicated than just doing a z-test or a t-test. You have to work with lots of different lists and interpret a lot of different things when you do it. But again, it's just a test that compares more than two samples at the same time. Next up, we're going to look at what's called Spearman's R. This is actually another non-parametric test. Spearman's R is used to compare ranked data. Ranks like first, second, third, that's what you're looking at for ranked data. And we want to know, are two different sets of rankings similar or different to each other? For example, if you ever watch like a beauty contest, or of course officially they call them scholarship competitions on TV, they will sometimes show you the ratings that different judges gave to the different candidates. And a very logical question might be, okay, so did the supermodel rate people differently than the football player did? And the answer is probably yes. They're probably looking at different things for their ratings. That's comparing two different sets of rankings, though. Who was their first ranking, who was second, who was third? Another possibility, you know that there are many different polls that'll show you who the top teams in different sports are. And you might be interested to know, for instance, was a coach's poll and a sportscaster's poll different? A lot of times it'll be the same teams, but they have the order mixed up a little bit. And a logical question will be, well, are they significantly different or just a little bit different? Key thing about Spearman's R, you can think of that R standing for ranking. It is always like first, second, third for Spearman's R. Next one I actually mentioned earlier, but we didn't really do it. It's what's called nonlinear regression. And the idea of nonlinear regression is you're looking at patterns that aren't lines. You remember those scatter plots you did in the regression chapter. What we cared about there is how close to being in a straight line were they? There are, however, lots of patterns that aren't lines. I actually mentioned a few weeks ago the idea of a sine regression where things go up and down, like the temperature goes up during the day and down at night. That's a definite pattern, but it's not a straight line. Another kind of example that comes up is what we call a quadratic regression. It makes what we call a parabola or a U shape. And another one that's really quite common is what we call an exponential regression. In an exponential regression, you have things that start small and very rapidly get very big. Would be like if you had a pair of rabbits and they started going at it like rabbits, and suddenly you got lots and lots of rabbits. That would be exponential growth. It's also the kind of growth that we've seen with things like COVID-19. There's two other things on this list, and the next one is the one I personally know the most about. It's what's called multiple regression analysis, and the reason why I know the most about it is when I was in grad school, this is basically what my main graduate project was about. So you guys have learned about linear regression, where you plug in a number for x and you try and predict what y is going to be. For instance, there was a question on your quiz last week where it gave you a formula that Michigan State used to take people's ACT scores and try and predict their grade point average. Well, that's nice, but you guys know there's a whole lot of things that might affect grade point besides your ACT score. And in fact, almost every real life problem, there's more than just one cause and one effect. There's lots of things that go into it. What multiple regression does, and it's the thing you'd want to write down, like if you choose this one for the test, is multiple regression uses many predictors to estimate an outcome. So back when I was in graduate school, one of my professors, a good old boy named Dr. Davidson, he did research on what did predict success in college. And he knew also that like ACT might sort of, but not really very well, and there might be some other things that would predict it better. Dr. Davidson actually came up with 37 different factors that he thought might have some effect on college grade point. I'm not going to list off all 37, but I am going to mention a few of them. Some of them included things like family income. Rich kids tended to do better than poor kids. How old a student was entering college. Typically, adult students do better than people of traditional college age. Things like ITEDs, the state competency scores, had the absolute lowest effect of all the things he predicted, and I bet most of you guys knew that. Something that had a very high effect was the number of activities that a student was involved in. People that were involved in lots of activities tended to have better grades than people that weren't. And if you've been in a lot of activities, you know that when you have lots of activities, you've got to learn time management. And that was just about the top effect for any of the ones he looked at. Other things were things like the budget of the school, the parents' marital status, how many brothers and sisters they had, the academic load, how many hours they were taking, and the size of a community. It's interesting that in Mississippi, students from larger towns did better than those from small towns in rural areas. In some places, like the upper Midwest, the opposite of that is true. Sometimes big school districts actually do not do as well as rural areas. Well, he spent a lot of time figuring out which of those were the most important, and initially he came up with a list of 12 out of those 37. Later, he actually pared it down to 5. And he had his grad students come up with a formula that could be used to take those possible variables and predict a student's GPA. We then programmed that formula into a bunch of graphing calculators and gave those to the recruiters that went around to high schools. And they asked some questions of the people they talked to, looked at it quick and said, well, if you go down to Hattiesburg, you can probably expect to get a 3.2 or whatever the GPA might have been. Then the following summer, the actual work that we did was we went back and we looked at the results and how accurately they did predict GPA. And we found that about 80% of the time, we actually could predict it within about a quarter of a grade point, which was way better than any one of those factors did on its own. So the big idea here is that multiple regression, you use lots of inputs to predict some result. The last one is not what I really expect you to pick for the test, but it is another of the main things that can come up in statistics. It's called calculus-based statistical theory, and it's really what makes the class you're in different than a class that a math major might take. The more advanced a statistics course is, the more likely it is to include a lot of calculus. There's two main ideas that come up in calculus, and both of those can be applied to statistics. One of the topics that comes up in calculus is what are called derivatives. And derivatives, what you're looking at is how things change over time. And one thing that can change over time is statistics. And you can use that form of calculus to figure out how things change from day to day, week to week, year to year. It's actually that kind of math that they're applying to come up with those formulas that the government looks at to see what's going to happen with the coronavirus and whether we can open things up or whether we have to remain at home. The other big topic that comes up in calculus is what are called integrals or sometimes antiderivatives. And integrals, the main thing they're used for is finding areas. We actually worked with area earlier in the year. Remember all those problems where we were finding areas of different parts of the normal curve? What you did to do those is you looked up the answers in a table. Where that table came from was working out a bunch of calculus problems. And again, what a math major might do is have to do the work to come up with those. Be grateful that you don't have to do that. It's already been done for you. Again, on your test, what you're going to want to do is pick 2 or 3 of those things we just went through, and it really doesn't matter which ones. You'll be given a list, so you don't need to remember the specific names. But you got to just tell me in a sentence or so what it's about. You can say things like Spearman's R looks at rankings of things, and that's enough. That gives the idea of what it is. So there's one more video, and that's the one that talks about what you need to know for the test.